myself to take over. Thank you.
Right. Thank you, Andrew. Thank you, and thank you for letting me host this presentation. At GasSecure, we have developed a wireless infrared hydrocarbon gas detector aimed at the oil and gas market. The detector is battery powered, and therefore it is energy constrained. Also, the oil and gas industry has some very strict safety requirements. So one of our tasks in developing this detector has been to meet the requirements of the industry and still keep the power consumption of the detector at an acceptable level. Now, most of this presentation will be about safe wireless and wireless ISA100, but I would like to kick things off with how the detector operates and what, in our view, makes the optical design of the detector unique. Then I will go into the safe, what we've called safe wireless, which is the communication architecture that we need to be able to run a safe protocol on top, which enables us to have a CO2 classification. When we started out, our main customer, Statoil, insisted that we based our wireless communication on a standard and a standard in the 2.4 gigahertz range. That gave us some choice, but I'll say a few words about why ISA100 Wireless was chosen. Finally, I'll say a couple of words about the higher level protocols, because the detector does not operate in a vacuum. It has to interface with higher level control systems. We are at GasSecure the first company to develop a wireless gas detector, and the requirements are, as I said, CO2 certification. Also, what we needed to do was to have continuous monitoring of the environment. That's combined with the fact that we need 2 years battery lifetime, means that we needed a very tight control over the power consumption of the device. Also, the device needed a very fast response. 5 seconds is an industry standard, and so we needed to fulfill that also. Finally, and I will get back to how this is done, but the detector needs no recalibration, and this is we believe, a major selling point of our device. Now, the challenge, if you compare our device to existing infrared detectors, is that state-of-the-art detectors, infrared hydrocarbon gas detectors, use roughly 5 watts average power. Some more, some less, but that's a ballpark figure. In order to run this for 2 years on batteries with the top-notch batteries that you can get your hands on, we need to get down to roughly 5 milliwatts. So it's a 1,000-fold decrease in power consumption, which means that we needed to optimize power consumption both on the detection part and on the wireless part. So for the wireless part, the challenge was to have bandwidth enough to have quick response and low power consumption. This slide here shows a schematic view of the detector and how it operates. Now, starting from the light source, the light will emit the infrared through a measurement chamber. Here you can see the cloud, which indicates the gas, via a mirror and back into the measurement or the measurement electronics volume. Here it'll bounce off a a MEMS chip and back up to the photo detector indicated here in blue. The MEMS chip is the core of the detection part of the device, and it works on the following principle. It can be in one of two states, and this is controlled by applying a signal to the MEMS chip. And when in one state, it will reflect a wavelength corresponding to the wavelength where hydrocarbon gas is absorbs infrared, and in the other state, it will reflect up to the photodetector a reference wavelength. Now, flipping back and forth between these two states, we get using the same single source and single detector, we get both a measurement signal and a reference signal. And so we have a system that auto-calibrates. We don't need to compensate for drift in the source, for drift in the detector. We use the same source and the same detector, and it will, seeing as we flip this at roughly a kilohertz, the signal that we receive will be stationary, and so we have an auto-calibrated system. And this here is a picture taken of the actual MEMS device that we use. These, incidentally, are fabricated at SINTEF in Norway. And this here shows a cross section of the device, whereas the last slide was a schematic view. This is more a direct view of what goes on. And here you recognize the lamp, the mirror that will reflect the signal back, the MEMS chip on the far left side, and a photodetector which will detect alternately the reference signal and the measurement signal. Now, moving on to the wireless part. Again, the detector does not operate here in a vacuum, and there are other protocols and systems operating. And if you look at here, the top left corner of this slide, there's the safety controller from ABB, and this is where the signal will originate, will go down through the gateway and down to the detector, and the detector will send the measurement signal back up. On the backbone here, we have Profinet in our first implementation, and we also have Modbus TCP. In addition, obviously, we need tools for calibration and for setting up the system for system parameters. Now, it's a fundamental concept of functional safety that a safe transfer of packets is originated at the controller. So a safe request and a safe exchange of messages starts off at the controller, and it's bounced back, and there's a unique correspondence between the request and the response of safe packets. We need to get a safe response back to the controller in a maximum of 2 seconds from gas is detected. And we do that by setting up from the detector side a contract that makes sure that we have transmit opportunities every 2 seconds. We've limited the architecture to hops. This is not strictly necessary. We could have had more hops to increase the range. We decided to limit ourselves to 2 hops for power consumption purposes. The communication here goes over what's known as the gray channel. That is, we don't make specific assumption on the rate of packet loss and that type of thing on the channel. and the safe exchange of messages is from the between the controller and the detector, and so the gateway is not drawn here in this slide. The payload of the message that we send is gas concentration, status of the battery, and any error diagnostics that we might have. As I said, the multi-hop support is important. This is indicated in the right slide here, with where you can have a primary and a secondary path, so that messages will get to the gateway back and forth, even if a path is obstructed, and the 2-second latency from the node to the controller in the event of a gas leakage. Now the question is then, how do we reduce power consumption? Now the solution that we've chosen is to allocate more bandwidth uplink than downlink, because under normal circumstances there is no gas, and so the average communication requirement is low, and so we have a relatively low downlink bandwidth, average bandwidth, and we set aside bandwidth uplink for in the event that the gas is detected. Before we go into the modes of operation, I would just like to draw your attention, or rather remind you, of what is implied by functional safety. Now, this very important figure is from the ISA100 which defines functional safety, and there's a number of possible error conditions that need to be detected and handled by safe protocol. These are listed on the left, such as repetition of packets, deletion, insertion, resequencing, and so on and so forth. The mechanisms that any system needs to handle in case if it is to be CL2 certified is it needs to have the sequence numbering, timeouts if in case something goes wrong, a code name, and also data consistency check. That's the CRC with a sufficient number of bits. ProfiSafe over Profinet or Profibus, if you prefer, has all these meets all these requirements, and so that is what we chose as a solution. Now let's look just for a second at how this operates, and this is the core of the safe wireless. Now what we do, what we get is the controller will issue a safe request, and it will be received by the gas detector indicated here by the GSO1. Now, instead of responding straight away, the detector will hold on to the request. And in this figure here, it will hold on to it for almost 30 seconds before it responds. Straight after, it will get a new request, the X+1. It will hold on to it for almost half a minute, and then it will respond. So the exchange continues. Now, in the event of a gas, looking now over to the right figure, in the event of a gas detection, the detector will respond as quickly as possible. Given that it has uplink transmit opportunities every 2 seconds, it will not be more than 2 seconds from gas is detected until the packet is sent to the controller. And then after that, it will respond as quickly as possible to all subsequent requests. So to summarize the main points of the safe wireless, in order to reduce bandwidth, what we do is we have a non-symmetrical bandwidth allocation, more bandwidth uplink than downlink. Now the detector is armed once it receives a downlink safe packet, and it will respond to that safe packet either late when there is no gas or as soon as possible when gas is detected. Now then, moving on to why we ended up choosing ISA100. There are three main reasons why we did that, and I'd like to go through them quickly in turn. The first has to do with sensitivity. Excuse me. Sensitivity, there are different ways of defining sensitivity, and in 15.4 radios is defined as the received signal strength you need to get a packet error rate of less than 1%. Now, at the time when we chose ISA100, the modules that we could get our hands on, the wireless modules for ISA, had 6 dB better or lower sensitivity than the wireless ART modules that we could get. And 6 dB is important. 6 dB is a lot. 6 dB means that you at least theoretically double the range in line of sight conditions. And so that alone was reason enough for us to choose ISA at the time. Now, it's important to note that this is not an issue of protocol. It is a question of silicon and the way the radio was implemented, not of the stack itself. And new wireless HART modules have the same performance as ISA100. So that was sensitivity. Now, next issue is quality of service. In ISA 100, there's the concept of contracts. A contract will give a guaranteed time of packet delivery, known as phase, and also of bandwidth. You will request a contract, and once that is awarded, if there is no packet loss, well, that's what you're guaranteed. That goes for both publish and client servers. And the important thing is this is bidirectional, so that you get you'll have the same sort of packet guarantees downlink, both for bandwidth and for timing downlink as you do uplink. In wireless HART, there's a concept of the burst channel, which corresponds to the publish mode of ISA, and it's a command response type of exchange. But you do have accurate timing control of downlink packets. At least you did not at the time of when we chose chose ISA, and that's the way we perceived it at the time was problematic. Now, also there's the third reason, which is the fact that ISA is object oriented, whereas wireless is more command oriented. The modern and object-oriented design of ISA really facilitates the design of user type applications. So for us to implement a safe wireless using ISA100 was very easy. Wireless HART, on the other hand, is command response oriented. As I said, we do not have any HART commands for safe communication, and so that was difficult. It probably could have been done, but it would have been less elegant, and wireless HART does not lend itself easily to that type of application. Certainly not at this point. There are other differences. These turn out to be less important, but I'll mention them anyway. ISA100 supports fragmented packets. It turned out that that wasn't all that important to us because our packets are small, so fragmentation wasn't an issue. Excuse me. Wireless HART also supports slow hopping. Early on, that was part of our design. We've moved away from that, so that also turned out not to be important. But it's a more general type of design than wireless HART in that respect. Also, we have various variable length slots in ISA100 according to the standard. Also, that ended up not being critical, so that's not important. But it's a more generic than general standard. Finally, and this is kind of important, wireless ISA supports star networks, so nodes can be leaf nodes. At the time when we looked at wireless HART, the nodes had to be also routers, to be able to route for others. Now, seeing as you can have very small, very geographically very dense networks, you may not want to have mesh networks, but rather just one-hop nodes, one-hop networks, and that would lower the power consumption and increase the lifetime of the batteries. So that's an important issue also. Final note on the standards. Wireless HART, as I said, had no command for supporting safety. We suspect, without knowing, but we do suspect that at some point there will be amendments to the wireless HART specification so that they do support safety, at least if they want to. Be able to have seal-rated equipment over wireless HART. What we did probably could have been done using wireless HART. Would have been, as I said, less elegant, but we probably could have done it with slightly less control over the downlink timing. We are currently in the process of developing support for wireless HART, but so far that will be for non-seal systems. Finally, on higher level of protocols, as I said, the initial work was done on Profi-Net and Profi-Safe. On top of that, we use both Safe and the regular part of the stack, and we transmit in the Safe packets gas concentration, battery status, and any error status if there is any to transfer. Modbus also we use, and that will be we transmit there the same information and some additional stuff also. We know that a lot of our customers are interested in foundation field bus, and so that is now in the process of being developed, but we're not quite there yet. We're working on that as work in progress. One note also on where we are, say commercially, we have one trial installation at an oil rig in the North Sea operated by Statoil. So we have 20 detectors there currently operational, and we have other demo installations up and running also. So just to summarize what I've talked about, in modesty aside, we believe that we have the best performing IR detector on the market. It has extremely low power consumption and 2 years battery life. And important to note also, no recalibration is necessary. We did choose ISA100 over wireless HART, and if we had to choose again today, we probably would have done it over. As I said, we suspect that at some point wireless HART will also support safety in order to have seal communication over their wireless infrastructure. Safe wireless, I talked about that. We use some asymmetric bandwidth allocation. We use Profi-Safe on top of that because it supports all the four mechanisms that we need to support functional safety and CO2. And on the wired side, on the, if you like, the north side of the gateway, we use Profinet's foundation field bus is in the process of being developed, and should also be noted that we have done our integration with ABB, and as some of you might have noticed, that the old ABB logo is apparent in our slides, and that's why. And that's it. Well, thank you for your attention.
Thank you, Niels. We appreciate it. I'm going to go ahead and I'm going to open it up to some questions. So if anyone has a question they'd like to ask Niels, you can go ahead and use the chat feature and send it to me. This is Lisa Grau, and I'll go ahead and send those directly on to Niels, or go ahead and make those public if anyone would like to have any clarification or have any questions. Niels, I have one question. They're asking if you have a system diagram for the installation on the Stay Oil platform.
We have documentation there for what we've done with Statoil, but I have to discuss with Statoil first what can and cannot be released from that installation.
And then I have another email question on what the battery life is.
Battery life is 2 years. Now, that will be a typical battery life. What I excuse me, what I didn't say is that there's a potential problem with the mirror condensing. If you have condensing, well, if you have very humid and you might have to remove the humidity with heating. So we have heating elements in there, and that's one of the reasons why the wired systems use so much power. Now we heat them as the others do, but we do it on demand or when it's required, and so the exact duration of the batteries will depend also on the condensing and the status of the condensing. But 2 years is typical.
Niels, another question. Was there anything done to the application in the ABB controller to allow it to use the wireless data?
Nothing particular to wireless. It would have worked equally well what they did, equally well with wired.
And related to that, when it said that the integration with ABB, what exactly do you mean by that?
Well, the implementation on the ABB side was done using 1131 type programming, and that they hadn't done. So, you know, it was on our side. We had to get this up. And they had to they also had to do to transmit the packets and make sure that the CRC went okay, and there were minor problems in the integration. Normally, there shouldn't be. Normally, if we have an existing Proby safe application running that can decode our messages, there shouldn't be much to do in terms of integration. So that should be a very quick task.
Great. I have a question on the temperatures and if there's any issues with minimum ambient temperatures.
It was now.
Or what is the minimum ambient temperature for outdoor installation?
I believe it's -20, but I think I'll have to verify that. But I believe it's -20 in the current version.
Okay, great.
Yeah.
How often do you recommend cleaning the lens?
Well, cleaning the lens will have to be done on demand. There's that's one of the error messages that the detector will transmit, is that the lens needs cleaning, because we'll see that the infrared signal level is decreasing, and so we will know that the lens needs cleaning. But that the cleaning the lens will be the same for our detector, and as for the other IR detectors, they work on the same sort of physical principle. So we shouldn't be any different from the others.
Okay, another question. What range of hydrocarbons are detectable with this IR sensor?
What is meant by what range? It's optimized. It is optimized on
which gases,
methane. Yes, well, it will detect methane, propane, and the classical hydrocarbon. The ones that will absorb infrared radiation. So it's propane, butane, methane, and I don't know. I don't have the complete list in my head, but it's a general hydrocarbon detector.
Someone is asking if you can connect other ISA100 sensors, pressure, temperature sensors, to this network.
We haven't tried doing that yet, but there's no reason why that shouldn't work. So that should be possible, yes.
Is there a limit to the number of devices that can be connected?
Currently, that limit stands at 50, I believe, and that's yes. It was 25 at the first release, and now I believe that's at 50.
In the customer installation that you cited, can you describe the user experience, and has it detected gas, and what has been the benefit to them?
Well, it has detected gas, I believe, but when it comes to how they experience it, I believe Statoil should really be the ones that answer that question. I would like to, but I think that's not my role here to answer on their behalf. But what we did see, we saw that the range of the detectors was very good, and we covered most of the platform that you saw on one of the slides with only one hop. So that was a surprise to us, and I believe to Statoil also, that we had a very good coverage.
Another question, can the battery be charged in a hazardous area, or does the device need to be removed for a battery change? Sorry.
They can be changed. They can be changed in a hazardous area. So it's ATEX approved, both the detector and you can change the battery pack. There's a battery pack, so there are 2 batteries inside a pack, and you need to take the pack out and insert a new pack, and that can be done in hazardous area.
Great. I think was the cost the justification for implementing wireless technology, or what was the impetus there?
Well, why we chose to do it wirelessly? Is that the question?
Yes. Mm-hmm.
Well, gas detectors often need to be moved or redeployed, and having them wireless makes it very easy to move around. It's also a very important implementation cost if they're wired, because wiring, especially offshore, is extremely expensive. And so having it wireless is a great benefit, just both cost and utility for the end user.
Great. Are there any other questions from anyone? Go ahead and please submit to Lisa Grau. All right. I think that is it. Thank you, Niels. We appreciate you conducting the WebEx and sharing your information on safe wireless communications for ISA100 using infrared gas detectors. And thank you all for joining. We will go ahead and we've recorded this, and we'll go ahead and put it up on the ISA WCI website, and you'll all get a note to be able to see that. Thank you again.
Okay, thank you.